Hi, we ended our last video in the middle of Model 3 of our sequential multiple regression example. Let's pick up where we left off with the coefficients table. All right, so here's our coefficients table. We interpret this just like we have in all of our other models and analyses. Our regression equation for Model 3 is our predicted grades is equal to 0.010 plus 0.110 times mother's education plus 0.042 times school quality plus 0.023 times study hours. If we look at the unstandardized coefficient for study hours, we see that controlling for mother's education and school quality, a 1 unit increase in study hours is associated with a 0.023 unit increase in grades. However, notice that this is not statistically significant, with a t with 396 degrees of freedom equal to 1.369 and a p-value of 0.172. So we're not convinced this is actually real. Study hours doesn't appear to have an effect, at least in this model. And looking at the unstandardized coefficient for mother's education, we see that controlling for school quality and study hours, a 1 unit increase in mother's education is associated with a 0.110 unit increase in grades. This is statistically significant, with a t with 396 degrees of freedom equal to 5.790 and a p-value less than 0.001. Now, notice how the effect from mother's education has continued to change between Model 2 and Model 3. We'll come back to that in a minute. And finally, looking at the unstandardized coefficient for school quality, we see that controlling for mother's education and study hours, a 1 unit increase in school quality is associated with a 0.042 unit increase in grades, which is also statistically significant, with a t with 396 degrees of freedom equal to 2.450 and a p-value of 0.015. Notice its effect has also changed slightly in this case between Model 2 and Model 3. Now, let's look at how the regression coefficients have changed along the way from Model 1 to Model 2 to Model 3 using path diagrams. Because they're path diagrams, right? The values are going to be standardized betas. But with 3 variables, it starts to get a little busy. So I'll write the value for each path, but I'm not going to write the Greek letter next to it. But they're betas. They're the standardized coefficients from each of the models. We started with Model 1, in which we just had mother's education, right? And we saw that its total effect on grades was 0.357. Now, there were no other variables in Model 1 at all, so there couldn't be any indirect effects. So given the total effect is the sum of the direct plus the indirect effects, this is also the direct effect for mother's education in Model 1. When we added school quality in Model 2, we saw that its standardized beta was equal to 0.122. Controlling for mother's education, a 1 standard deviation increase in school quality was associated with a 0.122 standard deviation increase in grades. That's the total effect for school quality, right? Remember that? For clarity, think about it. It's the effect of school quality when we added it into the model, controlling for prior effects in the sequential order based on our model. And it's before we've introduced any additional variables that appear later in the model. The effect at this point in time, right now when we enter it, is the total effect for the variable. Now, there are no indirect effects for school quality in Model 2, right? School quality doesn't have an effect on some third variable that then has an effect on grades. The total effect is just the direct effect at this point, right? It's the impact of school quality controlling for or unrelated to mother's education. In contrast, we saw that with mother's education, that total effect of 0.357 split into the direct effect of mother's education, controlling for school quality, and the indirect effect of mother's education through school quality. In Model 2, the 0.324 direct effect is the effect of mother's education that's unrelated to school quality. It tells us that controlling for school quality, a 1 standard deviation increase in mother's education is associated with a 0.324 standard deviation increase in grades. Now in Model 3, we added study hours. The 3 blue paths reflect the 3 standardized betas from Model 3, right? Let's start with the new variable that we just added, study hours, right? Its standardized beta was 0.069. Because we've added it in this step, it's the total effect for study hours. That 0.069 is the effect that study hours has after controlling for the preceding variable. It's the effect that's unrelated to the preceding variables, in this case, mother's education and school quality, because we've already given them the credit for any shared effect that they have with study hours. And because it's the last variable in that sequential order of effects, it has no indirect effects, right? All of that 0.069 is a direct effect. The standardized beta at 0.069 tells us that controlling for both mother's education and school quality, a 1 standard deviation increase in study hours is associated with a 0.069 standard deviation increase in grades. Right? Now, let's look at school quality. Notice the path from school quality to grades has changed since Model 2. Now it's 0.119. Why? Well, that's because the total effect of 0.122 that we saw from Model 2 has now been split. Part of it goes into a direct effect that school quality has, controlling not just for mother's education, but also for study hours. And part of it goes into the indirect effect that school quality has through study hours. That 0.119 direct effect is the effect of school quality that's unrelated to both mother's education and study hours. The standardized beta of 0.119 tells us that controlling for mother's education and study hours, a 1 standard deviation increase in school quality is associated with a 0.119 standard deviation increase in grades. All right? Now, finally, notice how the effect for mother's education changed again in Model 3. That's because we've continued to divide that 0.357 total effect for mother's education. Part of it now is the direct effect of 0.299 that's unrelated to both school quality and study hours. And part of it's now split into 3 possible indirect effects that mother's education has on grades through study hours or through study hours, through school quality, or through both of them. Now remember, we'll learn how to calculate indirect effects later on when we cover path analysis. For now, that 0.299 beta tells us that controlling for school quality and study hours, a 1 standard deviation increase in mother's education is associated with a 0.299 standard deviation increase in grades. Now, why don't we pause for a moment and think about this? Do you see how we started with a total effect of 0.357, and we've now twice carved that up into more and more possible indirect effects, plus a direct effect that's unrelated to any of the variables that we added. It's kind of like dividing a pie up among more and more family members on the holidays. The total pie doesn't change. We're just carving it up among more and more people. Similarly, the total effect doesn't change. We're just carving it up into more and more slices, each piece of which tells us something about the relationship between these variables. Now again, don't forget that we're still not estimating the specific effects between our individual predictors. We'll do that in path analysis. And remember, the regression coefficients correspond to direct effects. They tell us the size of the specific direct effect in our different models. On the other hand, the indirect effects are calculated based on different combinations of paths. And again, we'll learn how to calculate those specific values later. But for now, it's okay just to understand what they are and how they relate to each other at a conceptual level, and how we carve it up, how we carve up that total effect in order to see the process through which one variable may be influencing the outcome all on its own, and influencing the outcome through other intervening or mediating variables. Again, at a conceptual level for now. And also remember, while the path diagram describes these direct effects in terms of standardized coefficients, it's the same effect as the unstandardized coefficients. One just describes the effect in terms of standard deviations, while the other describes it in terms of the raw units. But it's the same direct effect. It's the effect that a variable has, controlling for or statistically removing the effect of all the other predictors, which is also the same effect as the squared semi-partial, which just describes that same effect in terms of variance. They're all describing the same thing. I think I've said that enough times now, right? Now, as one final exercise before wrapping this up, let's quickly calculate the squared semi-partials and see how they compare in a Venn diagram, all right? So here's the semi-partial correlations for each predictor in Model 3. We just square each of them and we get the unique effect of mother's education by squaring the 0.269 to get 0.072. That tells us that 7.2% of the variance in grades is uniquely only related to mother's education. We square the semi-partial of 0.114 for school quality and we get 0.013. That tells us that 1.3% of the variance in grades is only uniquely just related to school quality and nothing else in the model. Finally, if we square the semi-partial for study hours, we square 0.064, we get 0.004, which tells us 0.4% of the variance in grades is only uniquely just related to study hours, and again, nothing else in our model. Now, let's convert this over to our Venn diagram so that we can fully appreciate the difference between these unique effects and the cumulative change in R² that we saw earlier. Because we're now only looking at the unique variances, notice the change in mom's education and school quality. When we entered each sequentially, the cumulative change in R² at each step reflected the total effect of each variable. But the unique variance only reflects each variable's direct effect after removing the effect of all the other predictors. As you can see, again, we're literally removing the variance that's related to the other predictors from each of the variables. Now, there's two things to notice here. First, did you see how the effect for study hours is the same here when we look at the unique variance of each predictor as it was when we looked at the change in R² and entered study hours in this final step? That's because, again, they're the same thing. when we enter one variable in a step, the change in r squared for that step is the unique effect for that variable in that step, right? But again, that only works when we add a single variable to the model in a step. And while we're at it, don't forget, this is also the total effect for study hours based on our model. And second, notice that model 3, the final model for our sequential multiple regression example, is identical to a simultaneous multiple regression based on the same set of predictors. Each would include all of the same variables, right? So the total r squared would be the same. Plus the regression coefficients in both approaches would be controlling for all of the same variables, so the regression coefficients would be the same as well. The only difference is how we get to this point. What we gain in sequential multiple regression, or alternatively what we lose in simultaneous multiple regression, is the information on the true total effect that each variable adds at each sequential step of the process. But to do that, you have to have a model that tells you the order for that process. So let's wrap up this video here. As we've seen, there's a lot of information at each step of a sequential multiple regression. In our next video, we'll circle back, that was an intentional pun, and examine how one can summarize the results for a sequential multiple regression step by step, properly leveraging the information regarding each variable's effect along the way. All right? See you then. Bye-bye.